right, for our lesson today, we are working on lesson 2 of module 5. Today we're going to be using rules for functions, but basically you're going to learn exactly what qualifies as a function, what does not qualify as a function, and you'll know you're successful when you can use like the rule that they give you to fill in a table, make predictions about outcomes, and learn if actually it's appropriate to assume a constant rate for different situations in life, okay? Let's go ahead and get started. All right, for our opening example, this is the table from example 2 of our last lesson, and then we have another table of values for the alleged motion of a second moving object. So if you think back to our last lesson, it gave us an example of a stone falling off of a building, and so that's represented by this table right here, and then it says this is a second object, okay? Does the first, it says make some comments about any troublesome features you observe in the second table of values. Does the first table of data have those troubles too? So let's look at this first table of data. We have the number of seconds. I'm just going to go through. So at half of a second, this thing went 4 feet. At 1 second, 16 feet. 1.5, 36. 2, 64. 2.5 seconds, this traveled 100 feet. 3 seconds, 144. 3.5, 196. 4 seconds, 256. So one thing I noticed is that these are all increasing by half. And on the other side, I noticed that these are all increasing over here, but it's different increments, okay? Last thing I noticed is that all of these values, they're different. No value has the same, like if it's a 1 and it goes to 16, no other number over here has a 16. So let's look at the second table and see if we see kind of similar things. So we have a half, it goes to 4, and then 1 second, it goes to 4 again, and then it says 1 second goes to 36. 2 goes to 64, 2.5 seconds, 80 feet, 3 seconds, it travels 99 feet, but also at 3 seconds, it travels 196 feet. So the troubles you should have noticed here, over here, we're not increasing in even increments, and we have values that are doubled. It says that 1 goes to 4, but then it says 1 goes to 36, okay? It says that 4 feet goes to 0.5, and 4 feet goes to 1, okay? And then we have a couple down here that are also have 2 values assigned to that 3. So this is what's troublesome here. It doesn't make sense. How can something that's falling at half a second, it fell 4 feet, and then at 1 second, it fell 4 feet again, and then at 1 second, again, it fell 36 feet. That doesn't make any sense, okay? These values are not making sense. So that's what we should have decided here, is that table 2, it has multiple y values assigned to the same x value. For example, 1 was assigned to 4, 1 was also assigned to 36. And that does not make any sense. So make sure you've seen that from this table, you've written it down, that is what's troublesome about this table, is that it has multiple y values assigned to the same x value. Okay, and then we're going to continue on. So from what we saw on that last screen, I'm going to tell you guys a rule about functions. Basically, functions for every input, this is our x, right? For every number we put into the function, there is only one output. or 1y. So they tell you to think of this as like this function machine. So that's what they've kind of created over here, a function machine. For every one thing that you put in, one x value you put in, you only get one y value out. You can't get something else, okay? So for that second table we just looked at, it's not a function because our x's had different y's, and you can only have one y for every x, okay? So we're going to use that new knowledge and kind of determine about, if some tables we see today are functions or not, and then we're going to use rules that they give us to complete our tables. So number 1, it says let d be the distance traveled in time. Use the equation d equals 16 times t squared. So this is our rule. So I told you last lesson that our rules are going to be getting a little bit trickier to create, and you'll see that this rule, it's kind of tricky, right? It's not like, oh, y equals 3 times x. Okay, this one says d equals 16t squared. So what we're going to do is we're going to find the distance by doing 16 times the t squared. So this is our t, and we're looking to find d. Okay? So we have 0.5 for our first t. So the distance equals 16 times 0.5 squared. Okay, so we're just going to solve that really quickly. 0.5 squared is the same as, well, 0.5 times 0.5. I'll do that in my calculator real quick. I got 0.25. And then 16 times 0.25. If I do that in my calculator, I get 4. So in half a second, we went 4 feet. Okay? And we're going to do that for all of these here. I'll do the next one, which is 1. So I have d equals 16 times 1 squared. 1 squared is 1. And so 16 times 1 is 16. Okay, and I'm going to go through and do that for all of these here. The next one is 1.5. Squared is 1.5 times 1.5, which comes out to be 2.25. And we do that times 16, and we get 36. And right now, I've done 3 so far. You can see my math. Just to save time, I'm just going to go ahead and add the rest in here, and then we're going to continue this question, okay? All right, so you can see that it did all that math. You can just go ahead and copy down those black ones that it dipped there as long as you understand how I got them. I just plugged them into the equation or the rule that they gave us. Now it says, are the distances you calculated equal to the table from lesson 1? You might not remember from lesson 1, but yes, these are the same values from that first table that we got yesterday when we did this first lesson. And then B says, does the function d equals 16 times t squared accurately represent the distance the stone fell after a given time? Or in other words, does that function described by this rule work? And it does. Yeah, it works every time. We got the correct rule here, and we applied it. So yes, it works. And it says to explain it. So the reason why I'm going to explain it is, I'm just going to say, this rule correctly calculated the distance at each time interval. Okay, let's go ahead and make sure you have that down. And the last thing I just want you to notice while we are still here is that for every single input here, every input, there's only one output. So this is a function. Every value up here, the t values, have one d value. There's not anything that's repeated up there, okay? All right, so make sure you have this down. Let me know if you're having any questions. Basically here we just applied the rule filled in our table, and then we made sure to let them know, yeah, this rule worked. It matched our numbers perfectly. And eventually you'll be able to determine that rule on your own, but not today. All right, number 2, it says, does this table, or can this table represent a function? And it wants us to explain. Well, let's look at our input and output. Remember, every input has to have one output. Okay, so let's look at literally every single row here and decide. Okay, we have a 1. This input gave us a 7. Okay, there's no other 1 here, so that one checks out. This 3 gave us a 16. Awesome. That checks out. There's no other 3 here giving us anything else. This 5 gave us a 19. But it says 5 also gives us a 20. So this is where we go wrong. We have 2 outputs for the same input. So no, this is not a function. There are 2 outputs for the same input. Okay, it says 5 gives you 19, but then it also says 5 gives you 20. And this does not make sense. Not a function. Okay? All right, moving on to the next one. All right, you're going to do the same thing here. I want you to determine if these are functions or not and give me an explanation. I'll give you a couple minutes to do it before we check it together, okay? All right, for the top one, you should have figured out that no, this is not a function. This 7 gives us a 15, and this 7 gives us a 10. So this is a no. There's 2 outputs for the same input. 7 gives you 15, and then it also says 7 gives you 10. This doesn't make sense. Okay, number 4, this one. As you're looking at it, you should have noticed that there are 2 32s. However, this is still a function, and the reason is these inputs were different. Just because the outputs were the same, that doesn't matter. Okay, the inputs still had different outputs. All right? Yes. Each input has only one output. Okay? Let me know if you have questions about that one. I know that that might seem tricky, but again, we can have the same output for different inputs. It just can't be the same input. Okay? All right, moving on to the next slide. Okay, number 5, it says it takes Josephine 34 minutes to complete her homework assignment of 10 problems. If we assume that she works at a constant rate, we can describe the situation using a function. Okay, predict how many problems she can complete in 25 minutes. So what I want you to do here is maybe create a table, okay, of the problems she does in the minutes that she does them in, and then I want you to do this prediction right here, okay, and then we'll go over it really quickly. So please make sure you get that done, and then we'll check it real quick. All right, so I created this little table with my X and my Y. I put, okay, in 34 minutes, she does 10 problems. In 25 minutes, how many problems does she do? Well, I need to find the constant rate here. And it said that she does work at a constant rate, so I can find that. So I'm going to find that by doing Y divided by X. In this case, my Y was a 10, my X was a 34. 10 divided by 34, this brings us to a decimal. If I do this real quick in my calculator, I get 0.29, and I'll just round it there. And then I can use that to find my Y value. So Y equals mx. So in this case, my m is at 0.29, so y equals 0.29 times, what's the x that I'm looking for? 25. And this is what we did in our first unit this year. So 0.29 times 25, I get 7.25 as my answer. Okay. So predict how many problems she can complete in 25 minutes. She can complete at least 7 problems, 7.25 problems. So that would go right here. All right. B says write a 2-variable linear equation that represents her constant rate of work. Well, I already did that. It's y equals 0.29x. It's a constant rate, so we were able to find our constant or our slope, right? It's a line. It'll be increasing at this rate the entire time. You could have also left this as a fraction if you wanted. Y equals, I think it comes out to, you could have done 10 over 34x, or you could have done y equals 5 over 17x when you reduced it. Okay, and again, this is review from our first unit. We're going to go ahead and move to the next one. All right, we're going to be using the equation we wrote in the part before, y equals 0.29x, or y equals 5 over 17x, to fill in this table below. So remember, these are our x values, these are our y values. So we're just going to plug it in. Y equals 0.29 times, I'm going to do this with 10, this is my x. Okay, if I do this math out, I get 2.9. Alright, next I'm going to do it for my 15. Y equals 0.29 times 15. When I do that in my calculator, I get, let's see, 4.35. And then I'm just going to pause and I'm going to fill in the last two for you because I'm not going to waste my time showing you the math when you know how to do it. Alright, so go ahead and fill those numbers in. So for 20 minutes, she gets 5.8 problems completed. For 25 minutes, she gets 7.25 problems completed, okay? So this is just how you would fill out this table. This is a constant rate. We're increasing, we're doing 2.9 problems every single minute. And we're going to move to the next one, okay? All right, here it says use a formula from part B to compute the number of problems completed when x equals -7. So remember, our equation was y equals 0.29 times x. So in this case, our x is a -7. So if I did 0.29 times -7, I would get -2.03. Does this answer make sense? Well, no, the answer does not make sense. And the reason being is that it's saying our time is negative. Time can't be negative. Remember, that's what our x represents. And we're not going to do a negative amount of problems. So the negative here is what is not making any sense to us. And then it says, for this problem, we assumed Josephine worked at a constant rate. Do you think that's a reasonable assumption? So think about yourself doing your homework. Do you think that you work at a constant rate, which means for every question you spend the exact same amount of time on? Is that reasonable? I mean, think of just like the work that you do in math class. Do we spend the same amount of time on every single question no matter what? No, we don't work at the same pace. We're learning different things. Some days our lessons are harder than others. Sometimes our questions require more work than others. So no, this is not reasonable. It is not reasonable at all. People work at non-constant rates. Very rarely does someone complete the same amount of work for every single minute, right? A machine does, like machines work at constant rates and you can definitely predict how much they're going to get done in a certain amount of time, but people don't. There's so many variables. You might get, lost in your thoughts. You might drop your pencil on the ground and then it takes longer to do your work. There's so much stuff going on. It's not reasonable to assume that anyone works at a constant rate. People work at non-constant rates, okay? Let's move on. All right, for your lesson summary today, these are the things I wanted you to learn, is that a function is a correspondence between a set. We call the things we put in inputs and the things we pull out outputs. Okay, these are your x and y values. Sometimes the phrase exactly one output is used instead of one and only output, but it means the same thing. Basically, there is one and only one output for each input. Okay? That means that if you put something in, it can only produce one value. All right? Furthermore, we can give a function a rule or a formula to predict those outputs that are happening. Sometimes we call these input-output machines like this below, and it kind of shows you what it would look like. For everything you put in, you only get one thing out. You cannot get multiple things out for that same value you put in. You can put a different value and get the same thing out, but only one input for every output. Okay? And if you get confused, come back to this page to look back at our examples before moving on to your exit ticket, okay? All right, using what we learned today, you're going to answer these following questions on your exit ticket that is going to be posted in Galileo. First question says, can this table represent a function? So remember, one input can only have one output. I spelled that wrong. Okay, make sure to explain. If you don't explain, you're not going to get full credit. The next, number 2, it says Kelly can tune 4 cars in 3 hours. If we assume he works at a constant rate, can we describe the situation using a function? So, 4 cars in 3 hours. I want you to write the rule. So I want you to find your constant, y divided by x. And then I want you to write your equation, y equals what? X. This is what I want you to put into your answer on Galileo. Okay? I want you to type your answer in there. Whatever's in that box is a number, by the way. Okay? All right. B says, let me put one more thing up there for A. Remember that time is always independent. So this is your X. This is your Y. Okay? B says, use the function you wrote in part A as the formula and complete this table. So you're just going to complete this table in Galileo. I will have you put your answers in for each of these. Okay, it says round to the hundreds place. I'll give you credit if it's really close. Okay? And last one. C says Kelly works 8 hours per day. According to this, how many cars will you finish at the end of the shift? So you're just going to answer that in Galileo. In 8 hours, how many cars will he do? And then D says, for this problem, you assumed that this guy worked at a constant rate. Do you think that that's reasonable? So I want you to answer that question for me in Galileo. Is it reasonable that this guy's working at a constant rate, that he finishes every single car in the same amount of time? Okay, that'll be your last question in Galileo for your exit ticket. When you finish your exit ticket, please complete your lesson reflection. You need to finish your exit ticket during class, and if you don't, you're going to get marked as off task for not completing it, okay?